Welcome to this explainer. Electricity is just one of those subjects that can instantly feel incredibly intimidating, right? We've all been there, getting bogged down by crazy theories, super dense jargon, and these really complex calculations. But what if we just completely decoded all of that? Today, we're going to transform that massive wall of confusion into a highly accessible, step-by-step explainer. We'll break down the invisible forces of electricity using some really simple, everyday physical analogies so you actually have the confidence to understand and even design a safe, DIY solar power system totally from scratch. So here is our roadmap for today. We're going to cover wires, rivers, and waves, break down volts, amps, and watts, and then master the watt-hour. After that, we'll look at series versus parallel connections, actually build a mock solar system, and finally, talk about staying safe with fuses. Let's get to it. Starting off with Section 1, wires, rivers, and waves. Let's just dive right into the actual flow of electricity. If you think about it, a basic wire is a lot like a simple water pipe. The metal inside is your conductor. That's where the electrical force actually flows. And that outer plastic covering, that's the insulator. It acts exactly like the walls of a pipe, safely trapping that electrical force inside so it can be transmitted over really long distances without just escaping everywhere. Now, when we push that force through our pipe, it usually takes one of two forms. Direct current, or DC, acts just like a river. There's a positive and a negative side. Think of a standard car battery. And the electrical charge flows continuously in one single direction. It goes from positive, right through your appliance, and straight to negative. But contrast that with alternating current, or AC. In an AC system, the positive and negative are actually switching back and forth incredibly fast. Now, the wire itself isn't physically vibrating in your wall, but the force inside it is oscillating. It's exactly like a wave moving across the ocean. The force of the wave travels across the sea, sure, but the actual water molecules, they just bob up and down. Moving on to Section 2, volts, amps, and watts. So now that we kind of know how electricity travels, how do we actually measure it? Well, we use three absolutely essential metrics, and to help understand them perfectly, we're going to stick with a really simple garden hose analogy. First up is voltage. Think of voltage as the literal water pressure inside your garden hose. Even when the hose nozzle is totally shut off, that pressure is constantly there, just ready and waiting to push. Voltage is basically your energy potential. It's also, by the way, your absolute easiest cheat sheet for compatibility. If you have a 12-volt battery, boom. Instantly you can hook up a 12-volt appliance to it. Next, we have amperage. If voltage is the pressure, amperage is the actual amount of water flowing, which directly tells you how thick your garden hose needs to be. The amperage rating is incredibly important. Why? Because it dictates the required size of your wire. If you try to push a massive amount of amps through a wire that is just way too small, all that energy simply can't fit, so it converts into extreme heat. And honestly, that is exactly how electrical fires start. Finally, we have watts. Watts represent the total amount of electrical power going through your entire system. You can think of it as the perfect combination of your pressure and your flow rate. And calculating it is super easy. You literally just multiply your volts by your amps. This really brilliantly illustrates how proportional these metrics actually are. So take a look. Panel A has high pressure at 10 volts, but very low flow at just 1 amp. Meanwhile, panel B has incredibly low pressure at 1 volt, but massive flow at 10 amps. The crazy thing? Both panels generate exactly 10 watts of total power. But here is the absolutely critical difference for you as a DIY builder. Panel B, with its 10 amps of flow, is going to demand a much thicker, much heavier wire to safely transport that power compared to panel A. Okay, we've got our core vocabulary down, so let's hit Section 3, mastering the watt-hour. To truly design a system that works, we have to introduce power over time into our equations. How long will this battery actually last? It is by far the most common question for anyone building a DIY solar system. Unfortunately, if you just look at the label on a battery at the hardware store, you're usually going to see an amp-hour rating. But as we just learned, amps without volts don't tell us the whole story. Comparing a 6-volt battery's amp hours to a 12-volt battery's amp hours, you're basically comparing apples to oranges. To find the real truth, we need one universal metric, watt-hours. Thankfully, finding watt-hours is incredibly easy. You just multiply your watts by hours. If your battery is rated in amp hours, simply multiply those amp hours by the battery's voltage to get your watt hours. And once you have this single unified number, planning becomes simple arithmetic. Seriously, if you have a 1,000 watt-hour storage battery and you plug in a 100-watt load, you just divide 1,000 by 100. Bam! It'll run for exactly 10 hours, no guesswork needed. Let's jump into Section 4, Series versus Parallel Connections. Because before we can start putting together our hypothetical solar system, we need to know the rules of the game for wiring components together. What's really fascinating here is how you can completely manipulate power just by changing your wiring strategy. If you wire components in parallel, which means connecting all the positive terminals into one wire and all the negative terminals into another, your voltage stays exactly the same, but your amperage actually increases, so your flow gets bigger. However, if you wire them in series, which is daisy-chaining the positive of panel 1 to the negative of panel 2, your amperage stays identical, but your voltage increases. In that case, your pressure multiplies. All right, the theory is set. Welcome to Section 5, Building a Solar System. We are officially ready to design from scratch and apply our brand new vocabulary to a real-world 12-volt scenario. We're going to follow a super logical 3-step design process here. First, we define the size of our energy storage tank. Second, we size the solar source needed to fill that tank. And third, we calculate the bottleneck connection that actually links the two together. So step 1, the battery bank. Let's say we're buying 3 12-volt, 155 amp-hour batteries and wiring them in parallel. 155 times 3 gives us 465 total amp-hours. Multiply that by 12 volts, and our total storage capacity is 5,580 watt-hours. Sounds great, right? But wait, there is a massive catch. Because these are sealed lead-acid batteries, discharging them all the way to 0 will absolutely ruin their lifespan. You can only safely discharge them to 50%. So we literally have to cut our number in half. That means our true usable battery capacity is actually 2,790 watt-hours. Moving to step 2, the solar panels. Let's say we found some panels online that output 101.1 watts each, and we buy 4 of them. That gives us a total array of 404.4 watts. Now, the big question, how fast will that array fill up our usable 2,790 watt-hour battery bank? Well, in the real world, solar panels typically only run at about 70% efficiency. So factoring that in, our 404-watt array will realistically output roughly 283 watts of actual power. That means recharging our lead-acid battery bank from empty to full will take just under 10 hours of solid sunlight. Step 3, the solar charge controller. This device regulates the power coming from the panels down to the battery, and they are rated in amps. So, we take our total solar array wattage, which was 404.4 watts, and divide it by our 12-volt system size. The result? 33.7 amps. This tells us we need a controller that can handle at least 33.7 amps. To be perfectly safe and to leave a little room for future expansion, we should definitely size up and buy a 40-amp solar charge controller. Look at that! We've designed a fully functional system. But hold on a second. Section 6, Staying Safe with Fuses. This is absolutely critical. If you connect an appliance directly to a battery capable of producing hundreds of amps without any protection, and a wire shorts out, well, all that energy turns into heat, and you will absolutely start a massive fire. Preventing fires is paramount here. Which brings us to our most crucial component, the humble fuse. A fuse is essentially an intentional weak point in your system. It's just a tiny wire housed in a casing that is literally designed to self-destruct. If your appliance shorts out and tries to pull a dangerous amount of amps, the fuse heats up, melts, and instantly severs the physical connection. It stops the flow of electricity dead in its tracks long before your wires can actually catch fire. The single most important number to remember when sizing a fuse for your DIY build is 1.25. It's so simple. Once you know the amp rating of the appliance you want to connect, just multiply that amp rating by 1.25, which gives you 125%. And that right there is the exact size fuse you need to buy to keep your system safe and completely bottleneck-free. Let's go ahead and lock in these golden rules for wiring safety. First, always use freely available online charts to match your wire gauge to your amp load and distance. Oh, and make sure you're using pure copper wire. Aluminum just can't handle the same loads. Second, size that fuse to 125% of your appliance's amp rating. Third, always connect the fuse on the positive wire as close to the battery's positive terminal as humanly possible. This protects the maximum length of wire. And finally, if you ever feel your wires while the system is running and they're physically hot to the touch, your wire gauge is dangerously small and you're just wasting precious energy as heat. Wow, we really covered a lot of ground today, from the water pressure in a garden hose all the way to sizing a real-world solar charge controller. You now have the fundamental vocabulary to truly read the world of electricity around you. So I'm going to leave you with this. Next time you look at that thick power cable running to your refrigerator, or even just the tiny thin wire charging your phone right now, ask yourself, how many volts, amps, and watts are silently flowing through those completely differently sized pipes this very second? Thanks so much for joining me on this explainer. Keep learning, keep exploring, and stay curious.